Have you ever stopped to consider the wastewater that your washing machine generates? Each year in Australia, our washing machines collectively produce enough wastewater to fill the MCG 150 times over. But what if we could halve this number? Well, I'd like to introduce you to Rinse Repeat. Rinse Repeat is a small wastewater recycling system for washing machines. When connected to a washing machine's existing hoses, Rinse Repeat will take half of the wastewater produced in a load of washing and treat it so that it can be safely recycled again into another load. My project began with the realisation that Australia faces immense challenges surrounding future water security. A literature review conducted early in the project identified that to cope with this challenge, recycling the wastewater produced around the home is projected to become increasingly important. Greywater is any wastewater produced in the home that is not from a toilet, and each day the average Melburnian produces about 92 litres of it. With treatment, this water is capable of being recycled and used again within the home. Greywater recycling at a basic level involves using it for irrigation, but if we consider a hierarchy of reuse applications, this is exceptionally low on the list. Greywater has the potential to be used in several higher level applications before it finally becomes irrigation water, but currently the technology to make this possible is inaccessible to the average consumer. Treatment systems that enable greywater to be reused in higher level applications around the home do exist, but with an average install cost of between $10,000 and $20,000, they are prohibitively expensive. The first factor impacting the cost is that these systems are designed to treat all household grey water, making them large in scale and complex to install. The second is that to reuse the treated grey water, significant alterations must be made to household plumbing. These findings led me to raise the following proposition. By framing grey water treatment in the context of a small indoor appliance rather than a large outdoor system, can I make high-level grey water recycling accessible to more households? Key inspiration for the project came from kitchen appliances and the way they adapt to spaces through their plug-and-play design. I was inspired by this adaptability and aimed to use it to redefine what a grey water treatment system could look like. Washing machines were targeted as the project context because they are one of the only water-using objects in a home where both the water inlet point and the drain point can both easily be accessed by a user. This holds enormous potential from a grey water recycling perspective, as it creates the fundamental context for a small treatment system to exist within. With this in mind, two primary design criteria were identified. The first was adaptability, as the object needed to be easily installed into existing laundries. And the second was safety, because any treated grey water must meet the safety guidelines identified by the government. Moving into design development, the first thing I did was to observe my washing machine and document the properties of the grey water it produced. A key finding was that a washing machine will take on clean water, then expel dirty water multiple times throughout a wash program. As time progresses and the machine moves from washing to rinsing, the water expelled becomes cleaner. Documenting the variability of the grey water led to a huge realisation. If I was to only extract the cleanest half of the grey water, I could minimise the complexity and size of the subsequent treatment system. I found that it is possible to identify this variability objectively by measuring the total dissolved solids of each grey water discharge. Laundries are typically small spaces with high variability to their design. To better understand how a treatment system could be oriented within an average domestic laundry, I put a call out on social media and received photos of 54 individual laundries. The optimal location for a small treatment system was identified as being on top of front-loading washing machines, as this would allow the product to fit 57% of the documented laundries. The next step in the project was to identify a suitable treatment technique. An extensive literature review brought to my attention an emerging lo-fi treatment technology known as biofiltration. This method involves passing dirty water through a vegetated sand filter to treat it. 4 different biofilter prototypes were constructed and tested with real grey water. Despite their huge initial promise though, after 2 months of testing, it was concluded that this technique was not suitable. With the biofilters a failure, a different approach was taken. Discussions with a chemist revealed that coagulation may be a suitable treatment method. This technique is used widely in industrial drinking water treatment and pool cleaning, but largely remains untested in treating grey water. Using pool cleaning coagulant and washing machine grey water, I conducted upwards of 50 individual cup tests to identify the most effective way to utilise this treatment method within my context. The results were incredibly promising and speak for themselves. I will describe in more detail exactly what the treatment process involves shortly. Based on all the work from my design development, I identified 5 further criteria to shape the final outcome. I identified that the prototype must be oriented on top of front-loading washing machines, categorise grey water based on total dissolved solids, extract only the cleanest half of the grey water, treat the grey water through coagulation, and supply tap water to the washing machine when the treated water runs out. I have been successful in producing a small-scale, semi-automated working prototype to explore how my design criteria translates into a real product. Though in reality, the prototype would be hooked up to a washing machine. For the purpose of the following demonstration, it is not. Its function is as follows. Rinse Repeat sits on top of any front-loading washing machine. It controls all water entering and leaving the washing machine through 4 separate connections. Ingoing connection 1, which receives dirty water from the washing machine. Ingoing connection 2, which receives clean water from the laundry tap. Outgoing connection 1, which sends dirty water to the laundry drain. And outgoing connection 2, which sends either treated water or tap water to the washing machine. Each time the washing machine expels grey water, it flows into Rinse Repeat via the categorization box. Here, the pollution level of the grey water is determined by a total dissolved solid sensor connected to an Arduino. If the grey water is too polluted, a solenoid valve automatically sends it to the drain. If the grey water is suitable for treatment, a separate solenoid valve automatically sends it to the treatment tank. Roughly 30 litres of water is suitable for treatment in any given load. This figure represents half the water use of a front-loading washing machine, and though the prototype can only process 1 litre of grey water, the treatment method has been successfully tested to work at 30 litres as well. The importance of this function cannot be overlooked. In literature, washing machine grey water is only ever recognised as one single entity, not as the sum of its parts. To the best of my knowledge, the automated categorization and extraction function I have designed is a first of its kind and is the key way that I can achieve such high treatment efficiencies in such a small object. This function is the key innovation of Rinse Repeat. In the treatment tank, a treatment solution made of the coagulant aluminium sulfate and water is dispensed. A motor then spins a paddle to mix the treatment solution and the grey water for 2 minutes. Over the next 12 hours, tiny particles of dirt clump together and slowly fall to the bottom of the treatment tank. The result is a volume of clean water above a thin layer of sludge. The treated water is accessed by a solenoid valve, which is positioned above where the sludge collects in the bottom of the chamber. Using an onboard flow meter and pump, Rinse Repeat identifies when the washing machine is being used again and sends it treated water. The treated water is visually identical to tap water and represents a huge change from its original state. When the treated water runs out, Rinse Repeat switches to supplying tap water to the washing machine. The final step is for the sludge in the bottom of the treatment chamber to be released to the drain via the discharge valve. I have been successful in meeting all of my identified design criteria. Specifically worth discussing are the 2 primary criteria. In terms of adaptability, the outcome is a success as it overcomes the prohibitive costs and complexity of existing systems. The plug-and-play approach to the outcome makes high-level grey water reuse a more accessible practice. In terms of safety, treated grey water must meet a number of water quality parameters as set by the government. It was not possible to test the treated water against all parameters, as the more complex tests require a laboratory. To overcome this, a combination of homemade testing equipment, consultations with a chemist, and referencing of available literature have been used to prove that the treated water is safe for reuse. Front-loading washing machines produce an average of 60 litres of grey water per wash. My experimental evidence suggests that with treatment, half of this figure is suitable for recycling in the next load of washing. The average Australian household does 260 loads of washing per year, meaning that if prototyped at full scale, Rinse Repeat could potentially save an average household 7,800 litres of water per year. This figure represents a 5% reduction to an individual household's water usage. Rinse Repeat makes high-level household wastewater recycling possible in a way that previously has not existed. The project has value as it provides an incredibly insightful exploration of what could be next in water-saving technology. In a future where drought and water scarcity are predicted to worsen, what this project ultimately provides is a meaningful step in the right direction and a source of hope for the future. Before I conclude, you'll notice that the form and aesthetics of this project have not been addressed. I had every intention of addressing this part of the project, however with 5 weeks until submission, I had a cycling accident and broke not one, but both of my arms. This was pretty much the worst case scenario, and if I'm honest, it's a bit of a miracle that I even managed to make it this far. So, what I am planning to do is come back to the project in my own time after graduation and finish the form and aesthetic work I started. This will allow me to fully realise the project and enter it into the next season of Design Awards. For now though, I'm going to have a long nap.